The question before us says a circular plate of radius 5 meters is asymmetrically loaded by a uniformly distributed load of intensity 3 kilonewton per meter square. The plate is pinned along the outer periphery and has a rigidity D, and the Poisson's ratio of the material can be assumed to be zero. It says you determine an expression for the deflected shape of the plate. So let's say solution. To determine an expression for the deflected shape of the plate, it says it's a circular plate. We have a circular plate. It is loaded uniformly this is the loading pressure, and then we have it being supported at the periphery. So if we cut a section through this plate, let's call it section XX, we'll end up with this. This is 3 kilonewton per meter square. So from the governing equation of plates, from the governing equation for circular plates, that is D over the R into 1 over R, D over the R into R to W over the R equals to Q over D. You can see this is equation 1. Now let's say the force acting on the plate, let's call it Q, and the force resisting the action, let's call it big Q. So for equilibrium, it means that the action of this force must be equal to the resistance, and this force is acting over the area of the plate must be equal to this resisting force acting at the circumference of the plate. So now, making Q the subject of the formula, we have Q over 2 dot R. I hope you are following. So now let's move to another slide so that I won't have to clean. Inserting the value of Q into the general formula, we obtain D over the R into 1 over R D over R into R, the W over the R equals to Q over 2D dot R. Let's call this equation 2. Let's always name our equation so that it will be easy to follow through. So now what we are trying to do to obtain the deflected shape, we just want to integrate this whole thing, this whole general formula until we get the value of W, this, until we get that value. So now integrating equation 2, we are going to integrate equation 2. Integrating equation 2, we have one over R d over the R into R W over the R oh, what happened? Okay, R W over the R will then be equal to Q. Mind you, we are differentiating with respect to R. I'm integrating rather R square over 2 plus the constant of integration A. Equation, you can call this equation 3. So multiplying equation 3 by R so that we can take out this 1 over R to make our integration easier, we say multiplying equation 3 by R and then integrating, we have when you integrate that, we have R the W over the R will be equals to Q over 2D with R raised to power 4 over 8 plus AR square over 2 plus B. We could call this equation 4. I'm assuming you know how to integrate. So now, to eliminate this R, we divide this equation 4, dividing equation 4 by R and integrating, we have W equals to Q over 64D R raised to power 4 plus AR square over 4 plus B log R plus C, which is the constant of our integration. We can call this equation 5. So we are here. But this doesn't make any sense to us now because we do not know the value of A, we do not know the value of B, we do not know the value of C. So assuming that this is a pinned support, the is a pinned support, applying boundary conditions for pinned support we have at the radius equals to 0, the W over the R will be equals to 0. At R equals to A or 5, which we have been given, at R equals to an arbitrary value, we have W equals to 0, and at R equals to A as well, moment of rotation mr is still equals to 0. So when we apply, you say from, if we come here, you will see that if we apply our first boundary condition to equation 4, if we apply our first boundary condition to equation 4, we will obtain the value of B. So if we say from 4, when R equals to 0 and the W over the R equals to 0, B will be equals to 0. Now, if we apply the second boundary condition to this equation 5, we obtain the value for C from 5 when R equals to A and W equals to 0. We have C to be equal to minus Q over 64 D A raised to power 4 plus A raised to power A square over 4. So we also know that our moment of rotation mr is equals to minus d into the square W over R square plus your Poisson ratio over R, the W over the R equals to 0. So now, but we have been given our Poisson ratio to be 0. Therefore, MR will be equals to minus D, that's our rigidity value, the square W over the R square. So to obtain the square W over the R square, we differentiate. Let me write that down. To obtain a value for the square W over the R square, we differentiate equation. Let's check the equation. Let me see. That will be equation equation 4. Yes, we differentiate equation 4. We missed a slide here. We differentiate equation 4. So differentiating equation 4, we obtain D. I advise before you differentiate equation 4, you divide through by R so that you eliminate that R in front. dW over this R square, we have 3 equals 3Q R square over 16D plus A over 2. Okay, so if we call this, well, what's the last equation we have? Our last equation is equation 5. So if we call this equation 6, and we call this equation 7 so that we can be recalling them. So inserting I spelled inserting wrongly, so sorry. Inserting the value of 7 into 6, we have minus D into 3QR square over 16D plus A over 2 equals to 0. So dividing through, by minus d all of this is just simplification. So minus d we have we are left with 3qr square over 16d plus a over 2 equals to 0. So making a subject of the formula, making a subject of the formula or of the expression, it's not an expression, of the equation, we have a to be equals to minus 3qr square over 8d, but r equals to a. Therefore, a equals to minus 3q a square over 8d. So inserting the values of a, b, and c into equation. What's the equation? I don't know. Let's check. This is equation what? Equation 5. Inserting the value of d into equation 5 is equation 5 into equation 5. We sorry, let's first, we have not obtained our value for um we have not yet obtained our value for c because we still have a there, right? So inserting our value into this equation, our value of a into this equation, let me name it as something so that it can be inserting value of a into equation 5 prime. Let's call it like that so that it will be, you can be able to follow. Do you get? So inserting the value of a into equation 5 prime, we obtain we obtain the value of c as c equals to 5qa raised to power 4 over 64d. I hope you are following. So to obtain the deflected shape, to obtain the deflection shape of the plate, we insert the values of A, B, and C into equation 5. So W becomes, the deflection shape becomes Q over 64D R raised to power 4 plus minus 3QA square over 8D. The R square over 4 plus 5Q A raised to power 4 over 64D. So at when radius, when r equals to 0, when radius of the shape equals to 0, our deflected shape becomes 5q a raised to power 4 over 64d. At maximum deflection, r equals to a, so w becomes q a raised to power 4 over 64d minus 3q a raised to power 4 over 32d plus 5q a raised to power 4 over 64. So you can also start by substituting the value of r as of 5 that were given from the beginning. So, but with that, this is the value for the deflected shape of our equation. I didn't bother to substitute the value of r because at the end of the day we still have this rigidity value that we don't know, and so but this is the general formula for the deflected shape of the plate. Thank you.